Welcome to another video in the Matrix of Time series. This one is called Motion, a Link of Space to Time. Hope you enjoy it. So motion is the engine of the universe. Whether we're looking at the cosmos, our solar system, we've got a planet spinning around its axis, a planet spinning around the solar system, our solar system spinning around the center of the Milky Way at about 500,000 miles per hour. If we start to look into matter and we get finer and finer, we look down at the atomic level, we see that everything is moving. There is just constant motion in the largest part of our universe to the smallest part of our universe. So it's a pretty important part. In our lives, we have motion. We fly in airplanes, we're driving in cars, or we take trains or subways. So this aspect of motion is an integral part of our lives. So the most common one is pi, which we know is 3.1416, and it goes on for forever. But this is a ratio of the relationship of the diameter to the circumference of a circle, and this we are all pretty familiar with. One that you might not be that familiar with is called the index of refraction. This is the ratio of the speed of light in one medium, air, to another medium, water. One of the ways you might have experienced this is if you're at a river or a lake and you put a stick in the water, and you notice that below the surface of the water, the stick bends. And you know that this is an optical illusion. Well, the amount that it bends is a factor of this ratio of the speed of light in one of the mediums to the speed of light in the other medium. The other effect that it also has, and this is, more easily seen in a pool, is that it tends to make the pool look shallower. And another ratio that we often don't think of as a ratio is the speed of light. And the speed of light, commonly in science and engineering denoted by the letter c, is 186,000 miles to 1 second, or 3 times 10 to the 8 meters to 1 second. And we can also look at this as a relationship, that of distance to duration, or space to time. Now, the speed of light is not commonly thought of as a ratio in science, but I think it's important at this point to just start to think of it in terms of this, because as we go further, you'll start to see how the speed of light or motion defines a relationship between space and time. So a constant ratio in motion. The constant ratio, that's the ratio of the distance to duration, stays the same. This can be thought of that the change in location in space for the same change in time always stays the same. So the first example would be the Earth rotating around its axis. Clearly, our day doesn't change very much. Scientists measure change in days, but they measure it in fractions of a millisecond. The rotation of our Earth around the Sun, again, pretty consistent. And the rotation of our solar system around the center of the Milky Way galaxy, also very consistent. So these speeds, that we've talked about them before, our sun moving around our sun at 67,000 miles an hour, our solar system moving around the center of the galaxy at 500,000 miles per hour, we're completely oblivious to all this motion, this incredible motion that we're experiencing all the time. We experience it as if it was just stillness. And so let's go back, look at another example, and that's when we take an aeroplane. And let's assume that we're up at cruising speed, we're running at about 600 miles per hour. And at that point, the pilot says that you're free to move around the cabin. And you move around the cabin, go to the restroom, talk to other passengers, as if the plane was still on the tarmac. You don't feel that you're going 600 miles per hour. And this is because this motion is constant. The moment the plane starts to slow down, we immediately feel that. And so this is a pretty interesting concept, that we're designed not to be able to detect or feel constant motion. But the moment that this motion changes, we do feel that. And let's look into that a little bit more. So let's talk about acceleration, which in this case is time squared. And this is what we do feel. So the most common aspect of acceleration that we can identify with is in a car when the light turns green and the car is accelerating, or when the light turns red and the car is decelerating. For those that have done skiing, you experience the pull of gravity in the form of acceleration as you go faster and faster down the hill, and when you fly during takeoff and during landing. So what is it that we're feeling? We are sensing the change in motion, that is, the change in the change of location divided by time. So it is change squared, which shows up in units of the acceleration as time squared. So the ratio of location to time is no longer constant, but is changing rapidly, which is changing sometimes rapidly, and we call this acceleration. And in fact, it is the rush of acceleration that we seek when we go on a fairground ride. Since it is acceleration that causes this rush of adrenaline in our bodies. So clearly our bodies are conditioned to not detect constant velocity. And it's only when the ratio of duration, distance in space, distance in space and duration in time changes that our body reacts to it. And luckily, this constant velocity does not cause rushes of adrenaline. Otherwise, we'd be a biological mess, because we would then react to the spinning of the Earth around its axis, the Earth around the Sun, and our solar system around the Milky Way galaxy. So, conversion of space to time and time to space. It's something we do every day, a lot of times unconsciously. So, let's go through an example and we'll see how we can do this almost automatically. Here we have an example of a driver that stops to ask a local how far away the gas station is. So the first answer that the local person can give, it is 5 minutes away. Go down this road, East Street, for 3 minutes, take a right onto Main Street, and then go for another 2 minutes on Main Street, and it'll be on your left. So what happened here? Probably not too aware of it, but a question about distance, because the driver asked how far away is it, was answered in time. The other option that the local had to give the driver is this answer, number 2. It's about 3 miles away. Go down this road, called East Street, for just under 2 miles. Take a right onto Main Street, and then go for just over a mile on Main Street, and it'll be on your left. So here we have a question about distance answered in terms of space. Now, if the driver had asked, how long does it take to go to the gas station, then answer 1 would have been appropriate. But we often switch because we consider space and time, especially with regards to motion, to traveling, interchangeable. The driver, who knows he has a low amount of gas, can use the 36 miles per hour to convert miles to minutes or minutes to miles. So here we see where the same question can be answered in 2 different formats, and often we do that. And this is because we can determine a ratio between space and time. In this case, we assume that the driver can average maybe 35 miles or 36 miles per hour. And if the driver wanted to know how much the distance was to answer 1, which was given to him in time because he has a very low amount of gas, and he can kind of relate more to how much distance he can go with the little amount of gas that he has than time. He can use this 36 miles per hour to determine that the first distance is approximately 2 miles and the second one is 1 mile. And the same if the answer was given in terms of answer 2, and he wanted to know how much time it was to go the 2 miles and the 1 mile. He can then convert it. So we can see where this motion, this ratio of space to time, can be used to convert units of space to time and time to space. Okay, so let's look at the relationship of space to time a little bit more specifically. So in the example that we gave before with the driver stopping for directions, we have a driver going 36 miles per hour, which was the equivalent of doing 3 miles in 5 minutes, as in an example. Now, what happens if the driver decides to go up to 72 miles an hour? They can do that in 2 ways. Either they can cover 6 miles in the same 5 minutes, or they can cover the same 3 miles in 2.5 minutes. So 72 miles per hour, or kilometers per hour for the rest of the world, but I'll stick with miles per hour for now, can be reached by either increasing the distance by 2x or reducing the time by a half. So what you notice is that distance space is equivalent to 1 over time. For instance, 2 times the distance has the same effect as 1/2 the time. 3x the distance is equivalent to 1/3 of the time. 10 times the distance is equivalent to 1/10 of the time, and so on. So time is equivalent to 1 over space, and space is equivalent to 1 over time. So we can say that time and space have an inverse relationship. And you can see that motion is the phenomenon that links space and time together in this inverse relationship. And so this relationship of time to space that's inverse through motion is really important, and we're going to come back to it, but there are a couple more concepts that I want to cover in a few more videos, and then we'll revisit this, but at least you've been introduced to it for now. So I think it's really important to give a basic introduction to the difference between scalar and vector, because that's going to become more and more important as we dig deeper into space and time in this series and in future series. So let's take a simple example. We have a stopwatch here, and we have a unit or a number, 5 minutes. Okay, we have a speedometer, and we have 95 miles per hour. So in both of these cases, these are called scalar variables because they have a magnitude to them. And in the last one, let's say that somebody told you they ran 2 miles. Again, you're like, okay, 2 miles. But none of these have any sense of direction. Let's go back to the time. In time, there's really no way to add direction. I know that typically we think of time as going forward, and so we go forward in times and backwards in times. But that's really, there is no limitation in physics between going forward in time and backwards in time, and that is not a direction. So for time, it is strictly a scalar variable with no direction. If we go to speed, let's say that somebody says, I went 95 miles per hour. Now, if they said I went 95 miles per hour north on I-44, now all of a sudden there's a sense of direction. And that magnitude has meaning in itself, but it's meaning relative to something. If it was just, a regular driver going 95 miles per hour, you could be alarmed because that, certainly they're going well over the speed limit. But if it's a race driver that said they were going 95 miles per hour, you could say, that's pretty slow. And regards to the runner, if that runner had said, I ran 1 mile east and then I ran another mile south, now you have direction, and that can be turned into a vector. So the two examples going 95 miles per hour running 2 miles can be turned into the form of a vector. So let's go back to the example where the driver stopped to ask the local how far away the gas station was. And the response was that it's 2 miles east and 1 mile south. So that's the form. The bold and italics form are the components of the vector. So typically, for completion, you could also add that it was 0 miles west and 0 miles north. So a space vector has directional components in it. Now I'll give you two examples. Typically these could be north, south, east, and west, or as all of you are familiar with either from your math days or your science days, X, Y, or Z. So as we mentioned in the directional component for the driver, it was 2 miles in the east component, 1 mile in the south component, 0 miles in the west component, and 0 miles in the north component. And so when you think in terms of vectors, they have components that give you a relation to, so that you can define direction. So going forward, our space is going to be considered a vector, so we'll call it vector space, and scalar, and time, which is a scalar variable, which has no direction, we'll label scalar time. So hopefully this slide gives you a little bit of a better understanding. Don't worry if you don't get it right away, because we'll be going over this in a number of different ways, and I think it'll start to gel for you. So the takeaway messages for this video is that motion is the engine of the universe. We're oblivious to a constant ratio of space to time. We feel the change in motion, which is called acceleration. Acceleration represents change squared or time squared. We can use motion to change space to time and time to space. And space and time have an inverse relationship. In the next video, we'll cover the following topics. We'll touch back on frame of reference, and we'll look into relativity in more detail. We'll look into how motion can slow down time and the equivalence for gravity. So I hope you join me in the next video. Thank you. If you'd like to watch more of the Matrix of Time videos, please hit the subscribe button and you'll be notified of new presentations. You can also visit my webpage at www.multidimensionaltime.com, and in there you'll see a reference to a book I've written that you might be interested in. Also, I have a page with technical papers. There's an intro paper, and there is a paper called Three-Dimensional Time and Consciousness in the technical section that'd be of interest to people with and without a technical background. And then the rest of the papers require an engineering or science background because they get quite technical. So again, please hit subscribe and join me in not only future videos of this Matrix of Time. There will also be other series related to space and time that I'll be doing in the future, and you'll at least be notified of those as well. Okay, thank you very much.